Hi everyone. So in today's video we will uh, talk about geometrical optics. It is also known by the name of ray optics. In today's video we will cover these points, some properties of light, reflection at plane surface, spherical mirrors, image tracing, and sign convention. So let's start with some properties of light. There are a few things that I want you to keep in your mind while uh, understanding, reading the chapter. Light, we know that light have two properties: wave nature and particle nature. We do not need to focus on either of them in this chapter. One more thing, light usually travels in a very short wavelength. Okay, now this was the first thing. The second thing is ray. The direction of propagation of a light ray light wave is called ray. So ray is nothing but a depiction of the um, direction of propagation of light. Now, third thing is light always travels in straight line unless there is suppose a thin film separating the media. At that place refraction or reflection or both could happen, or there is an obstruction in the medium. In this case, if the obstruction is shorter than the wavelength of light, in that case, the wave front, suppose this is the wave front of the light, this is the wave front of the light. The wave front tends to bend around the object and then keep moving. But since wavelength of light is usually very small, we can ignore all these phenomena. Okay, so I guess this is everything. Let's it was the properties of light. We have covered it. Let's go to reflection at a plane surface. Smooth plane surface. Now we all know that no surface is 100% smooth or 100% elastic. In that case, 100% reflection also is not possible. That's why at some places you may have seen in these salons you may have seen two mirrors placed in front of each other, and there is a tunneling effect. So why can't we see infinitely inside the mirror? This is the reason, because some of the light particles are absorbed by the mirror and turned into heat or something else, and that's why as the tunneling effect progresses, the image fades. Now suppose this is a mirror or a smooth surface, whatever you can call it. This is a light ray, just shot at it completely perpendicularly. And also I I should tell you about the uh, laws of reflection before we dive into image tracing. Laws of reflection. There are two laws. The first one is that the angle of incidence and the angle of reflection are always equal. Second thing is that the incident ray, the reflected ray, and the normal ray all lie in the same plane. Okay, so second one, let's explain the second law first. It says that suppose here is a and here is an object. It gave off a light beam, something like that. So, and this was norm. This ray was shot at exactly 90 degree at the mirror. So what happened is that this ray came, hit the mirror, and then traced its path back. So this is the normal ray. This object gave off this ray. So this we will call as the incident ray. Let's call the object S. Now the angle between the normal and the incident ray is called the angle of incidence and is depicted by I. Now suppose the ray got reflected something like this. So this is the reflected ray, and the angle between the normal and the reflected ray is called the angle of reflection and is denoted by R. So the first law says that angle I is equal to angle R, and we do not need to prove it because it is proven practically. The second law says that the incident ray, the normal ray, and the reflected ray all lie in same plane. So suppose this canvas that I am using to write everything on is a plane, then all these three rays will be in the same plane. So we do not need to prove this law also because it is proven practically. Now let's look at how an image is formed. So this is the front of the mirror and this is the back. Now let's say this object also gave another ray which came perpendicularly to the mirror. So the ray will come, incident ray. So the incident ray will come and reflected ray will trace its path back. Let's say this reflected ray, we trace it back, trace it back into the back side of the mirror, and let's take this reflected ray and trace its path into the back side of the mirror, and the point at which both these reflected ray and their trace meets will be the point where the image of the object will be formed. So it will to and suppose an observer is here observing everything. To the observer, it will look like the rays are getting di- diverged from here. So the observer will be able to look at the object at the back of the mirror. Now let's say this point is A, this point is B, this point is C, and this point is D. Then it is proven in geometry that triangle ABC is congruent to triangle BDC. And by this result, we can say that the distance AC is equal to the distance CD. What this result depicts is that the image of the object will form at the same distance behind the mirror at which it is put in front of the mirror. So this was all in reflection at a smooth plane surface. So we have covered reflection at a smooth plane surface. Now we will go for spherical mirrors. Also, one more thing I would like to add before we move to spherical surfaces. What if someone asks you, what about a spherical polished ball? What would happen if light ray is incident at this point? This is the radius. So at this point we will draw a tangent, and the same phenomenon as the plane mirror would occur here also. No exceptions. All the laws of reflection will be followed. Now let's come to spherical mirrors. See, Spherical mirrors are a part of a hollow sphere. So what happens is that we take a hollow sphere and take out a part of it, something like this, and we polish one side of it. So in this picture that I have drawn, if I have polished the convex side, the reflection will take place at the concave side. So it will be called a concave mirror or a converging mirror, because reflection takes place at concave surface. The same piece I take and I polish the concave side, then reflection will take place at the convex side. So it will be called a convex mirror or a diverging mirror, because reflection takes place at convex surface. Now there are some points that I would like you to keep in mind before we dive deep into mirrors and reflections and everything. That is some terms. Suppose this is a mirror and this mirror is a part of this sphere. So this sphere had a center. So this mirror will also have a center, let's say here, and this will be called center of curvature of mirror donated by C. Similarly, this sphere had a radius, so this mirror will also have a radius, and it will be called radius of curvature of mirror denoted by R. So this mirror is like an arc. If we straighten this mirror, it will look like something like this. So there will be a midpoint. So this mirror will also have midpoint, let's say here. This midpoint is called pole of the mirror and is denoted by P. Okay, and the line that connects the center of curvature and the pole is called the principal axis of the mirror. Okay, so these are some of the notations that I wanted you to keep in mind. Now we have got a general idea of spherical mirrors. Uh, we will now look at image tracing. And before image tracing, let me tell you about focus. Focus of a mirror. Suppose we have a concave mirror like this. This is our principal axis. Now, uh, this is suppose this is the center of curvature of the mirror. Now, suppose uh, an object is placed far, far beyond the center of curvature of the mirror, and for such an object, we will call that the object is at infinity. Not that it is actually at infinity, but as compared to the length of the center of curvature of the mirror, the distance of the object is far greater in magnitude. In that case, the rays that will come from that object will be considered parallel. And parallel to what? Parallel to the principal axis. Now, after converging, the point on the principal axis where the reflected rays will meet is called the focal focus of the mirror, and the distance between pole and focus is called focal length. Let's see the same thing on a convex mirror. So let's see the same thing on a convex mirror. This is our principal axis. This is our center of curvature, and parallel beams are shot at the mirror from from an object kept at infinity. Suppose these rays get reflected like this. Then the place at which tracing back of the reflected rays will meet is called the focus of the convex mirror. So, to the observer in this case, it would look like that the image, that the rays of the image are diverging from behind the mirror, and in the case of a concave mirror, to the observer it will look like that the rays of the image are diverging uh, in front of the mirror from the focus, both case from the focus. So this was all about focus of a mirror. Now we have image tracing. So, so before we dive into image tracing, uh, a very important concept that we all should know is paraxial rays. What are paraxial rays? Suppose we have a mirror, something like this. We have our principal axis, and here is the image. It can either be an object, it can either be an object or a source of light, and it is so small that the rays given by it are almost touching the principal axis, and all of the rays kind of, wait a minute, let me clean my screen, and all of the rays kind of fall directly near the pole. Okay, but so these rays, which are very close to the principal axis, are called paraxial rays, and in geometrical optics, or as we say ray optics, we always talk about paraxial rays only, and we do not consider any other rays apart from paraxial rays. But then you will um, you will have a question that if they are so close to the principal axis, how will we uh, do image tracing and find the focus or find the center of curvature, and so uh, if they are so close, how will we do the image tracing and make the images, form the images? So for that, what the educators and the writers of books did is that they zoomed this part. Now the object becomes like this, and you have your rays, and now you can do your image tracing. So what we have been doing and we have been looking at in geometrical optics uh, for so long are nothing but the zoomed out parts of the paraxial rays and the objects and the pole and the mirror. So in theory, uh, these are very small and the rays that are taken are very close to the principal axis. Now let's do image tracing. Suppose I have a concave mirror. This is my principal axis, and and an object is, suppose, let's take a point object. We have a point object, so it will give off a ray something like this. It will give off a ray something like this, and these rays will get reflected according to the law of reflection. This ray will also get reflected, and at the intersection of the reflected ray we will have an image. So if the if the actual reflected rays intersect, the image will be real. Now let's take a convex mirror. Similarly, let's take point object. It will give off a ray, it will give off a ray, and the rays will get diverged. But we see that these reflected rays have no way to intersect each other. So we will trace back their path behind the mirror, and behind the mirror where their traced path meet will be the object. Okay, so if the traced back path of the reflected ray intersect to form an image, that image will be called a virtual image. Now see, you can see a common thing here, and that is that all these all these objects are giving off rays that are diverging. Okay, and these objects are in proximity of the mirror, so we know that where the rays are coming from. But in some cases the rays always the objects always do not give off diverging rays. Sometimes they give off converging rays. And what happens is that, let's take an example. Let's take a concave mirror, and let's take a converging ray. In this case, what happens is that we do not know where the object is. Okay, we only know that the rays are converging. So by the laws of reflection, we will trace the reflected rays, and here an image of that object will form. But if we trace back the incident rays behind the mirror, we see that they intersect somewhere. Okay, now it is the incident rays that are intersecting and not the uh, virtual rays, not the reflected rays. If reflected rays intersect somewhere, real image, reflected ray, virtual image. What if an incident ray intersects? If a pure incident ray intersects, it will be real object. And if its traced path intersects, then it will be a virtual object. So for this image, this real image, this is the virtual object. So this is a very special case in which we realize that even objects can be virtual. So this is all that was in image tracing. We have done image tracing, and let's dive into sign convention. Okay, so to measure the distances like focal length, center of curvature, object distance, and image distance, we need sign convention. So it is taken as if the distance is taken in the direction of the light ray, it's positive, and vice versa. Or you can say, let's draw a mirror. We draw drew a mirror, This is our principal axis. What is happening to my iPad? So we have our principal axis. Finally, we have our principal axis. Suppose this is focus, this is center of curvature, this which is also called as twice the length of focus, and this is the virtual focus, and this is the virtual center of curvature, and this is this we can say 2f2. Okay, and this is a concave mirror, so this is reflecting surface, so light will come from here to here. In that case, every distance which is taken in this side will be positive, and every distance which is taken in this side will be negative. Or the second method is, you can consider this principal axis as x-axis, okay, and the pole as origin. So before the pole everything is negative, and after the pole everything is positive. If we have to take the um, size of the object or image, so any size that is above the principal axis will be positive, any size which is below the principal axis will be negative. So this is all about sign convention. Now let's compare some distances by drawing some image tracings. So let's take a concave mirror. Okay, center of curvature, focus, and our object. So this is V, this is U. Let's say A. Again, let's take concave mirror, focus, center of curvature, and this time our object here. Okay, now let's call it Just call this condition B. Now let's take a convex mirror. Focus, center of curvature, or object. Ray 1, ray 2 gets diverged, meet somewhere here. So this is V, this is U. Okay, and that special case that we saw, या फिर उसको रहने देते हैं क्योंकि we have already seen that special case. Now let's compare all the distances. Focus, center of curvature, U and V. A, B, C. So in case of A, focus is negative, focal length is negative, center of curvature length is negative, the object distance is from the pole is also negative, and the image, the real image that is formed by the intersection of reflected rays, that is also behind the pole, so that is also negative. In the case of B, focus negative, center of curvature negative, object distance negative, but image distance is positive because it is after the pole. And in case of C also, focus is negative, center of curvature is negative, object distance from the pole is negative, and the image distance from the pole is positive. So the sign convention works something like this. That's all for today. For this video, in the next video we will establish the relation between U, V and F, relation between center of curvature and focus, derive करेंगे इसको हम, and third thing is magnification. So if you stayed until the end, thank you so much, thank you very much for watching the whole video. And I'm not a teacher, I'm also a student, but I like teaching, so that's why I'm making all these videos. If you have learned something from this video, uh, I'm very happy, and stay tuned to watch the next videos. And if you have someone in class 11th, 12th plus ninth, 10th. These people who are aspiring, especially for Neet, can watch these videos, and that's all for today. Please like, comment, and subscribe, and stay tuned for the next video.